Hi, I'm Ben-Yaakov. This presentation is entitled Causes of Oscillations in Flyback Converters. I'm showing here a schematics of the generic buildup of a flyback converter. I'll assume it is working in discontinuous mode, that is DCM. And here we have the switch. There is a magnetic element, actually it's a coupled inductor. We have a output diode and then the load and a smoothing or filter capacitor. So this is the basic configuration of a flyback, which is very, very popular. And I'm assuming it is working in DCM. We'll talk about it in a minute. I'm going to go over the waveform of this generic ideal flyback converter. So let's start with the transistor turned on. Here it's turned on, VGS is on. The current starts to build up at the primary. The polarity at the secondary is such that the diode is not conducting, so the load is actually fed from this capacitor, a storage capacitor feeding the output during this time. And then we have the current building up. Here it is, the constant voltage on the primary. So we have a constant dI/dt. The voltage on the transistor is low, and there is no output current at this stage. Then we turn off the transistor. Here it is off. VGS is off. Obviously, the current will start flowing through this transistor. It will be turned off. And then the current at the secondary will start flowing through the diode. And this is because at the on time, current was going into the dot, and then to maintain the same energy in the coupled inductor or in the magnetic field, then the current here will also go into the dot and therefore through the diode to the output. Then it will charge the capacitor and of course also feed the output. So we see here the VGS is off, no current at the primary, and then we have the voltage on the transistor, the sum of V in plus the reflected voltage, because when the current is flowing here, this secondary winding is clamped to the output, and through this magnetic element, which also functions as a transformer, when we have a voltage here, it will be transferred to the primary, depending on the turn ratio. So we get here on the transistor the sum of V in plus this voltage, so this is this voltage here. Energy then is pumped from the magnetic element to the output. Eventually, the current will go down to zero. Here it is. This is the secondary. At that time, there's no energy stored in the element. There's no current here. So everything sort of stops. The voltage across the primary is zero because there's no voltage, no dI/dt. Everything is sort of idle. And this will be the time that the voltage on the transistor will be actually the input because the voltage here is zero. So this is the DCM, discontinuous conduction mode, in which there is a period, there is no current through either primary or secondary. Okay, so this is this time now, there is no current, or here, there's no current through the primary or the secondary. And this actually completes the cycle, and then it starts again with the on time. In reality, if we look at the waveform in a real system, this is a simulation, but it is pretty close to what you'll see in the physical system, in the hardware, when you run it and test it. What we're going to see here is the gate voltage, okay? And now we have a lot of oscillations here. Well, we see that when the voltage at the gate is on, the drain goes to low, the current is building up at the primary, and then we see the current starting at the secondary during the off stage and then dropping to zero, and this is now the idle time. But what we see is a lot of oscillation. During the turn off, we see here oscillation here at the top. We see oscillation here at the current of the primary winding. We see here oscillation at the output at turn off, we see it here. And then during the time the transistor is on, we see that the current is not smooth. Actually, there's some oscillation on it, which is then reflected to the output. And then we have, of course, this is again turn off. And then we have, during the idle time, at which there is no current at the primary or secondary, this is this time here or this time here, we have this oscillation, lower frequency. We see it at the primary current, and we see it also at the voltage of the MOSFET. Okay, so there is a waveform here, which is like a sinusoidal waveform, a lower frequency of oscillation. So the objective of this presentation is to explain what is causing these oscillations. Actually, we have three types of oscillation here, which are different. This will be of the lower frequency. This is intermediate, and this seems to be a very high frequency here. Okay, this is the time the transistor is on. So in the following, I'm going to explain each of these oscillations. So let's start with the turn off. That is, the transistor was on and then it was turned off. Now, the whole picture, or the real picture, is that there are some parasitics to the circuit. First of all, we have a leakage inductance, which I am showing it as if it is at the input, just for convenience of analysis and understanding. You could reflect to the output, but again, here it's more intuitively understood when it is on the primary. And then we have, this is the magnetization part. Then we have the interwinding capacitances here. And then I'm showing here a clamp. We need the clamp because without the clamp, and as we interrupt the current of the leakage, then the voltage here will start rising and it can reach a dangerous level to damage the transistor. So therefore we are using a clamp. I'm not going into the design of the clamp. The idea is to generate here actually a voltage. This is plus here and minus here, such that it is clamping the voltage of the MOSFET, of the drain, to this value. Okay, just to protect it. We can see it here. This is the time that we have the clamp, and then the voltage of the drain is actually a bit lower, and then we have this oscillation. Now at this stage, the diode is conducting. We are at the off after the on, so there is energy in the elements of the diode is conducting. I'm neglecting the voltage drop on the diode, and the output voltage is reflected to the primary. So here is a simplified schematics that shows just the element that will cause the oscillation. We have here the reflected voltage, so it's a voltage source which is clamping here the Lm. So this is a constant voltage across this dependent source, you might say. We have the leakage. We have the output capacitance of the transistor, COSS, here it is here. And then when the diode stops conducting, we have the capacitance of the diode. So we have now actually a resonant circuit. This is a short for AC because it's a voltage source. So we have a inductor and then two capacitors in parallel. Now the resonant frequency will be, of course, 1 over 2 pi and then square root of the inductance, which is this one, and the sum of these capacitors. And this will cause this oscillation here. We're talking about this oscillation here. We see here the voltage on the transistor, and we see, of course, the current through the primary winding. This is where the leakage is, or we have reflected it to it. And we also see it reflected to the output, which is at that time conducting, because we are just after the turn off, and there is a current at the secondary. Okay, so we see this oscillation, which is being reflected at these three places. So now zooming on this oscillation, I find that the frequency is 2 megahertz. Okay, so this is here 2 megahertz. By the way, the switching frequency is 100 kilohertz. So it's a higher frequency because the leakage is small inductance and the capacitances are really small. So it comes up to be 2 megahertz. So let's do some analysis on this situation here. The first thing I'm going to do is to repeat this simulation after adding an extra parallel capacitor to the MOSFET, 1 nanofarad. Well, the reason is that I can now run it and get another set of data, that is the graphs, and from which I can get the frequency, say. And then I'm going to get, therefore, two equations. One, the original one without the capacitor, the parallel capacitor, one with the capacitor. Having two equations, I can actually solve for two unknown, which is the output capacitance of the MOSFET and the leakage. Okay? So I can actually do this extraction from these two set of data. So if I add this capacitor, I see that the frequency drops. Well, this is clear because I've added the capacitor to the resonant network, and now it's about 1.5 megahertz. So the resonant frequency before adding the capacitor is 1 over 2 pi square root of the leakage and the total capacitance. And then after adding, it will be the same plus 1 nanofarad. And therefore, the ratio here is this the ratio of the frequency that I've measured, the 2 megahertz, 1.5 megahertz. And from these two sets of equations, I can get C sub t, the total capacitance, which comes to be 1.3 nanofarad. Okay. Now, I can also do some measurement in simulation to see what is the current that is passing through this capacitor during this time and the voltage. Both are sinusoidal or close to sinusoidal. Well, there might be some losses in the actual transistor. There are losses here because the capacitance is lossy, but I'm ignoring it, of course, and I'm not sure that in the simulation model it's taken into account. In any event, I'm ignoring it. So from the current going through the transistor and the voltage across it, which I'm showing it here, this is the current and this is the voltage. Assuming that they are again 90 degrees because of the phase shift of the capacitance, and looking at the amplitude, I can actually extract the capacitance. And the capacitance comes to be 1.6. Well, it's not exactly what I found. I found 1.3 for the total, but it's pretty close considering the fact that we are talking about a non-linear capacitor. And when you have a non-linear capacitor, you are sort of moving over this curve. This is the C out SS, this is the output capacitance, but this is small signal. That is, it is measured by actually biasing the transistor and be exposing it to a small signal. We're talking here about a larger signal, which is moving back and forth. So, although it's not exactly what I found, I think it shows that what we are talking about seems to be viable, and the circuit is indeed a resonant circuit, as I've shown, with the parasitic that I've indicated. Now, from these two equations, I can also get the leakage inductance, okay? And I can get it from the measurement without the 1 nanofarad, and it comes to be 4 microhenry. Okay, so this is something that I got from the measurement. On the other hand, in the circuit, I've put a coupled inductor with a coupling coefficient of 0.98. This is for the simulation circuit. Now, this translates to an equivalent circuit that looks like that, in which we have, this is, I call it the magnetization inductance, the leakage, and an ideal transformer. Okay, this is another representation of this coupled inductor. I'd say it's an engineering view of the situation, like a transformer, rather than the physics-based coupled inductor. Now, the value of this leakage, which we are talking about, turns out to be L1. This is the total inductance times 1 minus k squared. And lo and behold, it comes out to be 3.96. So there's a very good matching between the calculated leakage from the observation and measurement and what I'd expect from the fact that the coupling coefficient is 0.98. So let me move now to this stage here, which is the idle stage, I call it. That is, after the current of the secondary dropped to zero. There's no current really in the system except for the oscillation. There's no energy stored except for the oscillation again. And now let's have a look what is causing this oscillation, which is at a low frequency. Okay, we see it at the primary inductor, and then we see it across the transistor, because the transistor behaves like a capacitor at this stage because it's non-conductive. So the circuit we are talking about is the circuit. There's no output. It's not connected, although there is some capacitance at the output. I'm neglecting it. In this intuitive analysis, I have the total primary, and then I have the output capacitance of the MOSFET, and then we have the capacitance of the diode. Again, I'm neglecting what is really happening here because there is some effect, of course, but we're looking at the first order effect rather than the very fine details of the analysis. So here is this circuit. Now, the difference between what we had before and this one is that now L sub m is sort of released. Previously, during the off time that we discussed, there was a voltage here, voltage source, which was causing a short across this inductor. So now we've added inductor, so the total inductance is larger. Now, obviously, the frequency will be lower, okay? So now let's see what is this frequency. I can, by simulation, look at it. And here I'm measuring one cycle here of this frequency. And indeed, it is, obviously, it can be seen it's a lower frequency, but the value is 350 kilohertz. Okay, so this is what I'm getting now. Now, I would expect that the ratio between the frequency here, and this one will be related to the square root of the ratio of the inductances, because I'm assuming that the capacitance are the same. Now, we know what is the ratio, and the ratio is square root 0.2. So we would expect that the resonant frequency will be related to this frequency here, at which we have only the leakage, by a factor of 0.2, meaning 400 kilohertz. Okay, we measured here 350, we got here 400. Now, and again, we are not taking into account that this is a non-linear capacitor, and as the amplitude is increasing, the capacitance is actually increasing, the total capacitance, the large signal capacitance. So therefore, you would expect the frequency actually to be lower, which is consistent with what we see. So we have covered the oscillation here, which is just at the off time, while the secondary is conducting and the primary is not, and the transistor is off. We have covered this part here, which is the idle time. That is that none of the winding is actually carrying any current, and there is an oscillation between the coupled inductor element and the parasitic capacitances. And now let's move to this case here, the third type of oscillation. And this is when the transistor is on, voltage of it, of course, is low because we have the RDS on. Current is building up, but we see here oscillation again. Well, these seem to be very high oscillation. So what is the reason for that? Well, what is happening here now is that when the transistor is conducting, we are imposing the input on the primary, so it's a constant voltage here. The diode is not conducting because of the polarity of the secondary. We have the capacitance of the diode. We have a voltage here imposed on this part here because this is also a transformer. And we have the leakage of the secondary, which obviously, because it is a step-down element, then this leakage is smaller than the one at the primary. And we have a capacitance which is relatively small, just the diode. So therefore, the frequency of oscillation is very high. Now, I'm not going into the actual calculation of the numbers here in this case. I just add that what I did here, I actually reflected the leakage from the primary to the secondary just to understand what is going on here. And by this, we understand that we have oscillation between this secondary reflected leakage and the capacitance of the diode. And then, of course, this will be a much higher frequency because both of these are small values. Now, to prove that indeed this is the reason for the oscillation, I've put here now a clamp, an RC clamp on the diode. At high frequency, the capacitance is short and we have 220 ohm, which is masking the effect of the capacitance. We see here more of a resistor than a capacitance at a high frequency. So this should sort of decay or stop the oscillation. And indeed, when I run the simulation with this clamp, you see a very fine line here, rise of the primary current, meaning that we don't have this oscillation, we don't see it here, and obviously we don't see it at secondary, which is the origin of this oscillation in the case that there is a capacitance of the diode. So this brings me to the end of this presentation. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.